Dear students, now welcome back for the ninth session of this solution topic. So in the form of usually the colligative property that we have already discussed or what we have discussed in the previous session. In that we have discussed I think nearly two colligative properties called as the first one is lowering of vapor pressure and then the elevation of which one? Boiling point. Okay. So we left with only the determination or expression for the molecular mass of that particular solute with the help of elevation of boiling point. So what is that first elevation here? It is an increase in the boiling point of the solvent, or it will be the solution that has been done due to the addition of a non-volatile solute to a what solvent? Pure solvent. Means if I put a small amount of a non-volatile solute to a pure solvent, the BP of that particular solution goes on increasing, and that increase in boiling point is called as elevation of boiling point, or it is also called by another term that is called ebullioscopy. Okay. So apart from that, we can have the mathematical definition or the mathematical reasoning with respect to the EBP, elevation in boiling point. It's just the difference. What's the difference here? The difference in the boiling point of the solution and then the boiling point of the pure solvent is called as elevation of boiling point. That is mathematically delta TB is equal to TB minus TB naught, where TB refers to the boiling point of the solution and TB naught refers to the boiling point of the solvent. The difference of those two is called as what? Elevation of boiling point, or it is also called as ebullioscopy. So and then we have written the graphical representation related to the elevation of boiling point. That is, as if a non-volatile solute is added to the pure solvent, what happens? First the vapor pressure of the solution goes on increasing, and simultaneously the boiling point of the solution goes on increasing. That is, addition of a non-volatile solute to a pure solvent lowers the vapor pressure of the solution and simultaneously elevates or increases the boiling point of the solution. That is mathematically what we have mentioned. TB minus TB naught is proportional to P naught minus P. That is delta TB proportional to delta P. Means elevation of boiling point is proportional to the lowering of which pressure? Vapor pressure. So then we have applied the Raoult's law, and on neglecting the terms with respect to number of moles of a solvent and then the molecular mass of the solvent, we have derived that delta TB is directly proportional to N2. What is that? The elevation of boiling point depends or directly proportional to the number of moles of the solute particles with respect to a dilute solution only, and hence it is an example for a what property? Colligative property. Okay. So based on that, now we are going to mention or explain what is a molecular mass expression related to the solute with the help of elevation of boiling point. That is, expression for the molecular mass. Which one? Molecular mass of a solute using EBP. What is that EBP here? Elevation of which point? Boiling point. So there also with the help of the Raoult's law we have mentioned what is that? The expression for the molecular mass of a solute. Okay. So here by the addition of NV solute to a pure solvent. What have you mentioned? If I add a non-volatile solute to a pure solvent, the vapor pressure of the solution goes on decreasing, and then boiling point of the solution goes on increasing. That is what we have decided from the graph. That is, TB minus TB naught is proportional to P naught minus P, or it is P naught minus P divided by P naught also. Why? Because P naught is the vapor pressure of the pure solvent, which is found to be the constant for a given solution at a constant temperature. That is why instead of P naught minus P, I can write that as what? P naught minus P divided by P naught. Here this is called as delta TB. TB minus TB naught is called as what? Delta TB. It is proportional to N2 divided by N1 plus N2. What is that? This is called as RLVP. What is RLVP? Relative lowering of what pressure? Vapor pressure. Relative lowering of vapor pressure is equal to the mole fraction of the solute. Mole fraction of what? Solute. According to what law here? Raoult's law of RLVP, relative lowering of vapor pressure, which is proportional to N2 divided by N1, because for A dilute solution N1 plus N2 is nearly equal to which one? N1. It is a condition with respect to what solution here? Dilute solution. Means the number of moles of a solute is almost very small, or it is also negligible as compared to that of the total number of moles with respect to the pure solvent. Therefore, instead of N1 plus N2, I will mention nearly in the form of what? N1. Okay? Delta TB proportional to. So this is mentioned as W2 by M2 divided by W1 by M1. Why? Because we know that. What is that? Number of moles is colored by the formula mass divided by molar mass. Means N is equal to W by M. Therefore, N2 is equal to what? W2 divided by M2, and this one. What is that? N1 is equal to W1 divided by M1, which is also proportional to, on simplification for that, W2 M1 divided by W1 into M2. Okay? On simplification. Which is proportional to W2 divided by W1 into M2. Why? Because I have neglected what? M1. Why? What is M1 here? It's a molecular mass of the solvent is found to be constant with respect to the given solution. That is why M1 is constant. Here, what is neglected here? P0 is neglected. Why? Because it is a vapor pressure of the pure solvent. Similarly, we can have the M1 is also neglected. Therefore, because it is an example for a solvent. Only the solute is variable, solution is variable, but not the solvent. On that basis, delta TB, if I remove the proportionality sign, I will get a constant called as Kb into W2 divided by W1 into M2. M2 is equal to what? Kb into W2 divided by delta TB into W1. 1000 kb W2 divided by delta T into W1. So this is one format for the molecular mass. Or if solvent is expressed in grams, therefore M2 can also be equal to 1000 times the Kb W2 divided by delta TB into W1. So what this is? A final expression related to the which one? Final expression related to the which one? The final expression with respect to which one? The molecular mass of a solute with the help of which one? Elevation of which point? Boiling point. So what is M2? Molecular mass of solute. So here Kb is called, we can have the three different terms related to that. Either it is called molar elevation constant, or it is also called as boiling point constant, BP constant, or it's also called as ebullioscopic constant. What constant it is? Ebullioscopic constant. W2, we know that is a mass of a solute. Delta TB is nothing but the elevation of which point? Boiling point. And W1 is nothing but the molecular mass of which one? The solute. Molecular mass of the, sorry, one means it is solvent. Molecular mass of the solvent. So this is the final expression where we are going to know the molecular mass of a solute with the help of which point? Elevation of boiling point, which is given by 1000 kb W2 divided by delta TB into what? W1. Okay. So now, how to define this value of Kb? Also, we can mention this as delta TB is also equal to Kb into M also. There is another expression related to this. Here, M is called molality of the solution. What's that M here? It is the molality, not the molarity, it is molality. Why? Because we know that W1 divided by M1, we know that it is nothing but 1 upon N1, number of moles. Okay. And W1 if is expressed in kg, means instead of 1000, if I take only this value, what it becomes? It is only the what? Not the molarity of the solution, it is the molality of the solution. Therefore, that delta TB, which is the first value, is nothing but this one. What is that? Kb into W2 divided by W1 into which one? The M1. That is, here we can mention, what is W2 by M2? W2 by M2 is called as what? N2. Number of moles of a solute per kg of a solvent is nothing but delta TB is equal to Kb into what? This is actually what? N2. What is N2? Number of moles of solute in, W2 divided by which one? M2. W2 divided by M2 is nothing but N2. Okay. N2 divided by W1 means number of moles of a solute in kg of a solvent is called as what? Small m. What is that small m? Here it is called. It is the molality of the solution. Okay. So this is the final expression first. This is more important. That is M2 is equal to 1000 times the Kb into W2 divided by delta Tb into W1. Here W refers to mass, M refers to molecular mass, Kb refers to molar elevation constant or boiling point constant, or sometimes it is also called as ebullioscopic constant. What is that constant here? It is the ebullioscopic constant. Okay. So then delta Tb, already we know that it is called as what point? Elevation of which one? Boiling point. So now, how to define this Kb? Definition of molar elevation constant, or it is also called as the boiling point constant, or sometimes it can also be called as ebullioscopic constant. Definition of Kb. We can have the two different definitions related to this. So here Kb is called as either molar elevation constant or boiling point constant, or it is also called as ebullioscopic constant. Okay. Suppose in this case if m is equal to 1, what is m small m? Molality. If I put m is equal to 1 means can I say that Kb is nothing but delta Tb? Therefore how to define that Kb here? Molar elevation constant, m is called as what? Molar elevation constant is defined as the EBP produced. What is EBP? M is equal to 1 means Kb is nothing but delta Tb. What is Kb here? Molar elevation constant is defined as the what point? Elevation in boiling point produced when? How much? 1 mole of a solute is added to how much? Instead of that, I will directly write that as in molar of 1 mole of produced in directly only 1 in 1 molar solution. What is molar? 1 mole of a solute that has been dissolved or dissolved in which one? 1 kg of a solvent. Therefore, molar elevation constant is defined as the elevation in the boiling point produced in how much? 1 molar solution. Or if I make the extension definition for this, MEC is defined as, it is also the what produced? Elevation in the boiling point produced when? How much? What is the meaning of 1 molar? When 1 mole of a NV solute, what is NV solute? Non-volatile solute is added to 1 kg of the pure, which one? Solvent. What's the meaning of that? It is nothing but 1 molar solution. What is 1 molar? 1 mole of a solute is added to what? 1 kg of a which one? Solvent. What is the elevation in the boiling point produced is called as MEC. What is MEC? Molar elevation constant, or it is also called as the elevation in the boiling point constant, or sometimes it is also called as what constant? The ebullioscopic constant. Okay. So that is about the definition of which one? Kb. So here, unit of Kb is, what's the unit of Kb here? It is Kelvin kg per mole or Kelvin per molar. How much produced? Elevation in the boiling point produced. Elevation in the boiling point means it is called Kelvin. Okay? Per 1 molar. What's the meaning of 1 molar? 1 mole of a solute that has been dissolved in 1 kg of a solvent. Therefore, I can express that in the form of either Kelvin kg per mole or Kelvin per directly the which one? The molar. So here Kb for water, the universal polar solvent, you have to remember that value 0.512 either Kelvin kg per mole or it may be the Kelvin per molar. That is a very important numerical that we have to remember, preferably for the pure solvent that is called as water. Okay. So also Kb can be calculated as, how it can be calculated as Rm1 Tb naught square divided by 1000 times the delta H of vapor. So there is no derivation here, just we can know the value of which one? The expression for the Kb. What is that Kb here? It is the molar elevation constant or elevation in the boiling point produced, or it is also called as the ebullioscopic constant. So mathematically Kb is equal to what? Rm1 Tb naught square divided by 1000 times the what? Delta H into Vp. So here R we know that it is gas constant, or it is also called as a solution constant. M1 we know that it is a molecular mass of a solvent. Molecular mass of a solvent. Tb means the boiling point of that solvent. Boiling point of that solvent. Here delta H of Vap is called as enthalpy of vaporization. It is also called as heat of vaporization. Enthalpy of vaporization, sometimes it can also be called as heat of which one? Vaporization. Okay. So this is about the second colligative property that what we have discussed in the form of which one? The elevation of which point? Boiling point, or it is also called as ebullioscopy. Okay. So now we will move on to the third colligative property, that is called as the depression in freezing point. What's that? Depression in which point? Freezing point. Okay. Let's move on to the third one. Let's have the third one. Depression of freezing point, or it can also be called by another name, cryoscopy. This is having a symbol of delta Tf. Delta Tf. Okay. When the freezing occurs, if the liquid, if it starts to get heated, it starts to get boils, its vapor pressure increases, and when that vapor pressure of the solution is, or the given liquid is going to be maximum, that is called as which point? Boiling point. Similarly, if the same liquid is applied with a decrease in temperature, as the temperature decreases, whatever the vapor pressure of the liquid, that also goes on decreasing, and it reaches a minimum, and that minimum vapor pressure temperature is called as what? The freezing point. Therefore, how to define this? Temperature at which the vapor pressure of the liquid is found to be the minimum, it is called as what point? Freezing point. When liquid start to get increased with temperature, means it is converted to a next state called as the gaseous state. Suppose if the liquid gets decreased with temperature, means it is converted into solid. There we have discussed what is at boiling point, the temperature at which the liquid and the liquid and the gaseous phases can coexist, and that particular temperature is called as boiling point. Here, as if we are decreasing the temperature, means liquid is in equilibrium with the solid, that particular temperature is called as freezing point. Therefore, this also a temperature at which the liquid and the solid phases of the same substance can coexist, combinedly exist. In case of boiling point, we have mentioned liquid and then the gaseous phases of the same substance can coexist, means it is called as boiling point. But here, as if I am decreasing the temperature, decrease in temperature converts the liquid into what state? Solid state. Therefore, the temperature at which the liquid and then the solid phases of the same substance can coexist is called as what point? Freezing point. Okay. Then what is depression of freezing point? It is very similar to that of the lowering of vapor pressure, or it is just quite opposite to that of which one? The elevation of which point? Boiling point. So here we are having the first definition related to this. It is the decrease in the freezing point of solution produced when a NV solute, non-volatile solute, is added to a pure, which one? Solvent. When a non-volatile solute is added to the pure solvent, the vapor pressure of the solution goes on decreasing, and that is called as a lowering of vapor pressure. If the same non-volatile solute is added to the pure solvent, the boiling point of the solution goes on increasing, that is called as elevation of boiling point. And just opposite to that, the same addition of a non-volatile solute to a pure solvent, it decreases the vapor pressure of the solution, and that point is called as depression of freezing point, or it is also called by another name, cryoscopy. What scopy it is? Cryoscopy. Or we can have the another definition according to the mathematical concept. It is the difference in the freezing point of a pure solvent and the freezing point of the respective, which one? Solution. In lowering of vapor pressure, the difference in the vapor pressure of the solvent and then the solution is called as lowering of vapor pressure. If it is a difference in the boiling point of the solution and then the boiling point of the solvent, then it is called as elevation in boiling point. But here again it is reversed. What is that? It is a difference in the freezing point of a pure solvent and then the freezing point of the solution. Mathematically, what we can have mathematical representation related to this? Mathematically, so here DFP, what is DFP? Depression of which point? Freezing point is nothing but delta TF, which is equal to TF naught minus TF. This is a mathematical expression or the definition related to the depression of which point? Freezing point. So here what is TF naught? It is FP of a pure solvent. What is TF? It is a FP of a given solution. So the difference in the freezing point of the pure solvent and then the solution that has been formed is called as what point? Depression of freezing point, which is also called as what scopy? Cryoscopy. Okay. So now, how to have the graphical representation related to this particular depression of which point? Freezing point. Now you have to prove. To prove DFP is a which property? Colligative property. What do you have to prove now? The depression of freezing point, we have to prove that it is an example for a what? The colligative property. Colligative property means we have to prove that it property of a physical property with respect to the dilute solution. It depends only upon the amount or number of moles of which particles? Solute particles, but not upon its chemical nature or it may be the size. Okay, so that we will do now. So here, so this is y-axis where we are having its what pressure? Vapor pressure. What pressure? Vapor pressure. This is called as FP. What is FP here? It is a freezing point. T. T, that is called as FP. Okay. As usual, this is the vapor pressure curve with respect to the pure solvent, and this is the vapor pressure curve with respect to the solution. Already we have mentioned. Why? Because addition of a non-volatile solute to a pure solvent decreases the what pressure? Vapor pressure. Therefore, the vapor pressure of the solvent is higher compared to that of which one? The vapor pressure of the solution. And also, as the temperature increases, the vapor pressure of not only the solvent but also the solution goes on increasing. But as if I want the freezing point now. So what happens? when I decrease the temperature relative to this. Suppose if I increase the temperature, it reaches the what pressure? Atmospheric pressure, and the corresponding temperatures are called as which point? Boiling point, that we have discussed previously. But here to get a what point? Boiling point. We have to decrease the temperature. Okay? So here, this is in the liquid state. If I move, it reaches the boiling point, that is the gaseous state. But here to get a solid state, this gets decreased, and suddenly it gets decreased like this. Okay? This particular temperature where we are expecting the sudden break relative to this is called as TF naught. What is TF naught here? It is the freezing point of the pure solvent. Freezing point of the pure solvent. Similarly, as the temperature decreases, whatever the vapor pressure of the solution, that also goes on decreasing and reaches this point, and this is called as a sudden decrease in this one is called as TF. What is TF here? It is again what? The freezing point of the solution. TF naught is the freezing point of the solvent, and TF is the freezing point of the which one? Solution. Okay? If I come back and retrace its path, this is called as P naught. And this is called as P. What is P naught and P? P naught is the vapor pressure of the pure solvent, and P is the vapor pressure of the solution. Okay? So therefore, what we can conclude by this particular graph here? What we can conclude from this? So here, as if from the graphical representation, what actually it is clear here, because we are proving that it is an example for a what property? Colligative property. Okay? Here, from graph, addition of NV solute, what is NV? Non-volatile solute to a pure solvent. Which solvent? Pure solvent. First, decreases the vapor pressure of solution and also simultaneously decreases the FP of the given solution. But in the previous graph, what you have mentioned, the decrease in the vapor pressure of the solution is simultaneously increases with the boiling point of the solution. But here both freezing point and then the vapor pressure goes on decreasing. First decrease the vapor pressure of the solution, and also it decreases the freezing point of the solution. That is, TF naught minus TF is proportional to P naught minus P. It is obtained from the graph. What is this? TF naught minus TF is proportional to what? P naught minus P. What is TF naught minus T? It is the depression of which point? Freezing point. What is P naught minus P? It is called as a delta P. Okay? It is also proportional to P naught minus P divided by P naught. Why? Because for a given solution, what is the vapor pressure of the pure solvent? It is constant. Which is variable? Solute is variable, solution is variable, but not the which one? Solvent. Therefore, what happened to the vapor pressure of the solution? As it is in a proportionality sign, it is remaining the constant. Which is proportional to, as usual, we know that it is N2 divided by N1 plus N2. This is by the application of what law here? Raoult's law. Because what is this? RLVP. What is RLVP? Relative lowering of what pressure? Vapor pressure. And this is equal to the what fraction? Mole fraction of the solute. R. What is this? Delta TF. What is delta TF? Depression of which point? Freezing point. Then it is proportional to N2 divided by N1. Why? Because for which solution? Dilute solution. What is N1 plus N2 is nearly equal to N1. Means we are neglecting the number of moles of which one? Solute, because the amount of the solute is very, very less as compared to the higher amount of the which one? Solvent, because it is strictly the what solution that we are referring? The dilute solution. R. Delta TB proportional to N2. Again, means what I am neglecting here? N1. Why? What is N1? Number of moles of a pure solvent. Because with respect to the given solution, solute is variable, solution is variable, but not the pure solvent. Therefore, N1 is neglected. So therefore, how to mention this? As the depression of freezing point varies directly to the which one? Number of moles of which particles? Solute particles with respect to what solution? Dilute solution. Hence it is an example for a what property there? It is a colligative property. Means for a physical quantity, to prove it as a what property? Colligative property. First it has to depend only on the number of moles of the which particles? Solute particles, and it is strictly applicable with respect to what solution? The dilute solution. Okay, so that is delta T of proportional to N2 with respect to the dilute solution, means it is an example for a what property? Colligative property. Okay, so then we will have the expression for mm of a solute, molecular mass of a solute, using DFP. What is DFP? It is the depression of which point? Freezing point. So as you, there is the same case that we have already experienced in case of the which one? Elevation of boiling point. It is very quite similar. The difference is M2 is equal to 1000 times the Kf W2 divided by delta Tf into W1. There is a small change here. There, in case of elevation of boiling point, instead of Kf, there we have mentioned the Kb. There, in that case, it is delta Tb. Now it is found to be the delta Tf. That's the difference here. M2 is what? Molecular mass of the solute. W2 is mass of the solute. What is W1? Mass of the pure solvent. Then what is delta Tf? Depression of which point? Freezing point. What is Kf now? Now it is a different term. Okay. So what that Kf is now? Here Kf is now mentioned as, here Kf is given by 3 different names. There we have mentioned it is molar elevation constant, but here it is molar depression constant. In the second we have mentioned that in the form of boiling point constant, but here it is called as freezing point constant. Freezing point constant. There it is called ebullioscopy, that is why it is called as ebullioscopy constant, but here it is cryoscopy, hence it is also called as cryoscopic constant. Cryoscopic constant. So that's the difference here. Molar elevation constant for Kb, molar depression constant for Kf. Boiling point constant is Kb, freezing point constant is Kf. Ebullioscopy constant is Kb, whereas this is called cryoscopy constant is called as Kf. Okay. Now, definition of Kf. How to define the Kf? And also, I mentioned another one. Delta Tf is equal to Kf into M. Kf into M. The same expression what we have done. Here M is called as molality of the solution, not molarity, it is the molarity. Therefore, how to define this? Same definition. If I put M is equal to 1, can I say that Kf is equal to delta Tb? The same definition. What is that? It is the DFP produced. What is DFP? Depression in the freezing point produced in 1 molar solution. Which solution here? It is the 1 molar solution. Means the molar depression constant is defined as the what? Depression of the freezing point produced in how much solution? 1 mole of the solution. It is the DFP produced. What is DFP? Mole depression in freezing point produced when how much? 1 mole of a NV solute. What is NV? Non-volatile solute is added to how much? Same. 1 kg of the pure solvent. Because 1 mole in 1 kg is nothing but 1 molar. Means the difference in the, depression in the freezing point produced in 1 molar solution is nothing but the depression in the boiling freezing point produced when how much? 1 mole of a solute. Which type of solute it is? It should be a non-volatile solute that has been added to how much of solvent? 1 kg of solvent. There the boiling point gets increased, that is why it is called as elevation. Here the freezing point is decreased, that is why it is called as depression in freezing point. And finally, unit of same Kf is very similar to that of either K kg per mole or K per molar. Means we are having the unit of, it is similar to that of kb. What is that? Kelvin kg per mole, or you can simply mention that as Kelvin per how much? 1 molar or Kelvin per molar. And the value of K for water, H2O, it is found to be 1.86 Kelvin kg per mole. What's the kb for water? It is 0.512 Kelvin kg per mole. That is, you have to remember that, because the most universally accepted polar solvent is the water. The value of kb for water is 0.512 Kelvin kg per mole, whereas the K for water is found to be 1.86 Kelvin kg per mole. Also, the expression with respect to Kf is given by RT1 Kf naught square, RT1, sorry, RM1, sorry, RM1 Tf naught square divided by 1000 times the which one? Delta H of freeze, or you can use the fusion also, freezing or fusion, whatever it may be. Enthalpy of freezing, or it is also called as enthalpy of which one? Fusion. As usual, what is R? The universal gas constant, or now here it is called as what constant? The solution constant. M1 is the molecular mass of the pure solvent. What is Tf naught? It is the freezing point of the pure solvent. And delta Tf, delta H of freezing is nothing but enthalpy of freezing, or sometimes it is also called as enthalpy of which one? Fusion. Okay. So this is how we are having the third colligative property in the form of which one? The depression of which point? Freezing point. Okay. So now I left with only one colligative property, that is called as osmotic pressure. We have discussed the three colligative properties like lowering of vapor pressure, elevation of boiling point, and finally the third one is, that is the depression of freezing point. Now we left with only one, that is called as which one? The osmotic pressure. Okay, so that we will discuss in the next session of this particular chapter, that is called as solutions. Okay, so thank you.